Hi class, welcome to lecture 4.5, which is basically me going over your test guide for exam 4. I will go over parts 1 and part 2, and before I go over part 2 I'll even talk about some of the equations. Now for part 1 we're really just going to go over some basic standard deviation type problems and then get into some maybe slightly more complicated risk versus return type of questions. Let's take a look at this first one, and you'll see you find a certain stock that has returns of 12%, negative 21%, 19%, and negative 15% for 4 of the last 5 years. The average return on the stock over this period was 5.5%. What is the standard deviation of the stock returns? So what you'll see there is that you had 5 years, but I only gave you 4 returns, right? So you need to figure out what that fifth return is. How do we calculate an average? Well, the most basic way that we're going to calculate an average is going to be just take all 5 of those returns, add them up, and divide by 5, right? Now we know that equals 5.5%. So we can set up an equation like I've done in step 1 where you put all of the returns, including x, in the numerator, divided by 5, set it equal to 0.055, and then you solve. Now, what's the first thing you do algebraically? First thing you're going to do algebraically is multiply both sides by what? 5, right? So you multiply both sides by 5, and that's why below you'll see that 0.275. Well, that's what you get when you multiply 5 times 0.055. Now, what about the x minus 0.05? Where did that come from? Well, that just came from me adding up all of the numbers in the numerator, right? And so I got, you can't add x into there, so you got x. All the rest added up to negative 0.05, so I wrote it as x minus 0.05. Now, what would you do now algebraically? Now you're going to add you're going to add 0.05 to both sides to cancel out that negative 0.05, and that's why you get x equals 0.325 or 32.5%. Okay. Now, once you know that, you can do something very simple, which is get the standard deviation. Now, it looks complicated, but it's very simple. Now, to say it, what you would say is you're going to get the sum of the squared differences between the actual returns and the average return and divide that by n minus 1. Okay? That sounds like a mouthful. So let's just take a look. If you look, what you'll see is standard deviation, which is nothing more than that little sigma squared, okay, is, well, actually, that's variance, and then you'll have to take the square root of that to get standard deviation. But nonetheless, to get variance in step 2, what you will do is you will plug in each one of those particular returns and subtract it from the average. Okay, so the first return was 12%. You subtract it from 5.5% and you square that, so that's that squared difference. And then you're going to add the next one, which is going to be a negative 21% subtracted from the average squared. And then you add in the 19% subtracted from the average squared. And then you add in the negative 15% subtracted from the average squared. And then you add in that last one, which we've just found in step 1, which is 32.5% minus the average squared, all over your n minus 1, which is going to be 4. Okay. Now, some ways of finding variance, they would just tell you to put 5 there or just put n. For finance, we're going to do n minus 1, and just trust me, and we'll leave that math topic alone or leave it for a statistics class later on. Once you get variance, though, you do have to realize that variance is the square of standard deviation. So you'll have to take the square root, okay, of the answer you got in step 2. And that's where this 22.78% came from. Now, a lot of you say, well, that's a lot of math, and there's a real easy chance that I can make a mistake. Well, I do have good news for you, especially if you've listened to this lecture, because you can get out your BA2 Plus calculator, and you can hit second 7. I'll repeat that, second 7 on your BA2 Plus calculator. And when you do that, you're going to get x01 to appear. Now, when that comes up, what you're going to want to do is plug in your first return. So I would put in 0.12, hit enter. Then I'm going to hit the down arrow, and it should say y01. Now we're only using one set of returns here, so I'm going to skip over that and go to x02, and I'm going to put in 0.21 negative, enter, and then I'm going to skip over to x03 using the down arrow. I'm going to put in 0.19, enter, skip over to x04. I'm going to put in 0.15 negative, enter, and then in x05 I'm going to put in 0.325, enter. Okay. Now you have to do step one with your before you put the information in your calculator. No matter what, because you don't know what that fifth return is. But if I just gave you the 5 returns, then you could start off and do this entire problem simply using your calculator. Okay, now once you have this information in there and it's locked in there, okay, what you're going to want to do then is you're going to want to hit second 8. I'll repeat that, second 8. And that's, if you look above that, it should say stat for statistics, right? So 7 is where you put your data in, 8 is where you put in your statistics, and it'll pop up LIN for linear. Just move on past that with a down arrow. N should say 5, okay? You'll get your X bar. X bar is the same thing as your average return in this case, so that should say 5.5% or 0.055. Now, then you're going to come to SX, okay? And that is the standard deviation that you're going to want. So there's your answer right there. Super fast, right? Calculators are a wonderful thing. Now, make sure you use SX if you do use the calculator in this manner. Why? Because hit the down arrow one more time, and there pops up the sigma X like you see on my test guide. Well, the calculator doesn't know that that's not that I use sigma X. Sigma X is if you decided to use n in the denominator, but we like to use n minus 1. So remember that the correct answer is going to be SX, not sigma X if you use your calculator. Okay, so it's very important. That's a very easy step, and I think that's very much worth your time. Now, once again, why is this even important? Because now that we have the average return and the standard deviation, we now can look at this stock from both an average return perspective and a risk perspective. Now let's kind of go back to some of the stuff we had from exam 3. Let's say you purchased a zero coupon bond 1 year ago for $322.18. The market interest rate is now 7.35%. If the bond had 9 years to maturity when you originally purchased it, what was your total return for the past year if the face value of the bond is $1,000? Okay, and we obviously knew the face value was $1,000. So this whole question, obviously you're like, this is, why am I learning about this for a stock test? Well, I'm just testing you to make sure you understand the concept of total return, which is super easy. So if you get this question on the exam, no big deal. Remember, with a zero coupon bond, one of the first things that you're going to do is you're going to solve for price, right? Find out how big of a discount it is. In this case, I'll tell you we're using semi-annual compounding on the test, and then you're going to have n equals 9 minus 1 times 2, which equals 16. Why was there a minus 1 in there? Go back up and you see you purchased that zero coupon bond 1 year ago, right? So that's where you took off the 1. All right, now this bond has a yield to maturity, an annual yield to maturity of 7.35%, but if we're going to use semi-annual compounding, you'll divide that by 2. Payment is going to be 0, okay? Obviously, why? It's a zero coupon bond. The future value is obviously going to be $1,000, right? So that's some exam 3 material right there. Now, you'll just hit compute PV and you'll get the price. How do I get total return though? Well, total return is nothing more than a percentage change. And if you remember from the last study guide, I talked about percentage change, and that is nothing more than new minus old over old. So in this case, we're going to do it with prices. So we take the new price of 561.33 minus the old price of 322.18 divided by 322.18, and you get a really big return of 74.23%. Okay, so it's pretty simple. That's how you would calculate total return. And it would work the exact same way with stocks too. Now let's take a look at number 3. Over the past 5 years, a stock has had an arithmetic average of 7.3%. 4 of those 5 years produced returns of 8.1%, 19.3%, 11.2%, and negative 14.1%. So what is the geometric average return for this 5-year period? Now, the arithmetic or arithmetic, however you want to say it, average return is what we know as the normal average, right? That's where we take all the values, add them up, and we divide it by the number. And so whenever you're getting an average, a lot of times you are probably mathematically getting the arithmetic average. Okay. Now, the geometric average is sometimes more accurate, especially in finance. It can be more accurate. And so what is it? Well, it is where you take 1 plus each of those values and you multiply them all, and then you're going to divide them by, or you're going to multiply them by an exponent of 1 over n. Okay? So, first thing we're going to do is in step 1, we're going to do very much like we did in step 1 on problem 1, where we're going to have to solve for x, right? X is in the numerator, it's one of the 5 values. So you're going to use the exact same algebra that we did up in there. So if you're confused, go back up and look at step 1 of problem 1, and you're going to get 12%. Now, in step 2, what we're going to do is then plug in that value. So each one of those numbers in there that's being multiplied is 1 plus one of the returns, right? So 1.081 is 1 plus 8.1%, 1.193 is 1 plus 19.3%, all the way down to the last return, which we just figured out, was 12%. So that's where you get 1.12. Multiply them all, and then raise them to 1/5. If you don't know how to do this, you can look and see on your calculator that you've got a couple different options. What I usually do is I will use the Y button and then use parentheses and do 1 divided by 5 in parentheses. But there's a couple different options. You could also use the Y button and just raise it to 0.2, which is the same thing as 1/5. But nonetheless, you're probably going to use the YX button. You've got some other options that you could probably do up there as well, but that's the main button I would use. Nonetheless, you should get 6.65%. And so what you've noticed here is that the geometric average return is less than the arithmetic average return. So these numbers are never going to be exactly the same unless all the returns are the same. If all the returns are the exact same, like they were all 12%, then you'd get the exact same answer. But the more volatility there is between these returns, the greater the difference is going to be between the arithmetic average and the geometric average. Moving on to number 4, we're going to throw an extra step into a problem like the first problem we did, problem number 1. We're going to figure out what the average return is and what the standard deviation is, which you can do steps 1 through 3 in your calculator using second 7 and second 8. Okay, or you can do it, I worked it out for you. Okay, but then when you get down to problem number 4, what they're really asking you is what range of returns would you expect to see 95% of the time? Now, on an exam, I'm going to do one of two things. I might just ask you just to do steps 1 and 2 and 3, right, and just get the average return and standard deviation. Or I might ask you to do it all and get all the way down and do step 4 where you find this range. Now, if I ask you to find the range, I could ask you to find what you would expect to see 68% of the time, and that would be 1 standard deviation. 95% of the time, which is what most scientific research uses for testing for significance, would be 2 standard deviations. And then 99% of the time, which would be 3 standard deviations. Now, since this question asks for 95%, that's a good chance I might ask for 68% or 99% on the exam. And if so, you will want to change the equation from r equals mu, which is that funny looking Greek symbol there, which just means nothing. Mu means nothing more than R bar, right, or average return. Okay, that what you got in step 1, plus or minus, and then you'd want to change that number 2 to either 1 if it's 68% or to 3 if it's 99% times your standard deviation, right, or sigma. So let me repeat that again. That equation for step 4 could change as far as the coefficient in front of sigma based on what range I'm asking for. If I'm asking for 68%, that would be a 1. If I'm asking for 95%, it's a 2. If I'm asking for 99%, it's a 3. Okay, in this case, I'm asking for 95%, so you want to find the range using both plus and minus. So it's going to be to find the positive side of the range, you're going to do 0.082 plus 2 times 0.1322, okay, and you get 0.3464. And to find the downside of the range, okay, you're going to take that average return and subtract 2 times 0.1322. Right? And where did I get these numbers from? Remember, mu, or the average return, came from step 1, and the standard deviation came from step 3. Okay, so my range here, 95% of the time, the stock is going to have a range from negative 18.24% to 34.64%. So I would expect my stock to be in that range 95% of the time. Now, over the past 4 years, large company stocks and U.S. Treasury bills have produced the returns stated below. During this period, inflation averaged 2.3%. Given this information, the average real rate of return on large company stocks was blank percent as compared to blank percent for Treasury bills. So in problem number 5, this goes back to the previous exam as well, because we're going to end up using the Fisher equation, right? If you remember the Fisher equation, then this should be no problem. The first thing you got to do is find an average for both large cap stocks and for Treasury bills. You'll just get those real quick, the arithmetic averages for them, add them up and divide by 4. So steps 1 and 3 below should be super easy. And then to find the average real return, you're going to use the equation that we had from we got that right out of the Fisher equation, right? So if you're confused, go back and look on your test guide from exam 3 and look at the one Fisher equation problem, and you'll see where this equation came from. Okay, and what we're going to do is basically subtract off inflation, and that's what we could do that real simple and get a real approximate answer. So, for example, if we know that the average large cap return is 12.5%, which we found in step 1, and we know that inflation is 2.3%, then I'm expecting an answer somewhere around 10.2%, right? Okay, so to get the exact answer, we have to use the Fisher equation, which is real return equals 1 plus the nominal return over 1 plus inflation minus 1. Throw that information in there, plug and chug, and you get 9.97%, which was pretty close to that 10.2%. Okay, with Treasury bills, let's think about the approximate rate real quick. If I know my average is 3.5% and I take off 2.3%, that'll leave me about 1.2%, right? Now let's find out what it is exactly, like we did in step 4 using the Fisher equation. All right, so the nominal rate is going to be 1.035, right, because it's 1 plus the nominal rate, and then in the denominator you've got 1 plus inflation, so you got 1.023. Subtract that 1, and then you're going to be left with 0.0117, which is 1.17%, very close to 1.2%. Okay, so that shows you that you can use the Fisher equation for both bonds, like we did before, and also now for stocks. Now we're moving into a little bit more meatier problem, and that because we're going to get into the idea of CAPM, right? And remember, CAPM stands for the Capital Asset Pricing Model, and we got into this discussion and the lecture as well, 4.1, talking about the security market line. So, a stock has a beta of 1.08. That's one of the things we need. An expected return of 12.42%. So now that's pretty much what we would have been solving for if we'd have used the CAPM. So that's going to be on the left side of that equation, and it lies on the security market line, which all that says is, hey, use the CAPM. A risk-free rate is yielding 3.4%, so we have that information. And you want to create a $5,000 portfolio consisting of stock A and a risk-free security such that the portfolio beta is 0.4. What you're going to notice is it doesn't matter what amount. I could have told you 1 million or 1 billion, and you're going to do this problem the same way. But you will use that portfolio beta in step 2. What we're missing here is we don't have the return on the market or the market risk premium. We need to know one of those two. And so in this case, we're going to solve first for the market risk premium. Remember that the market risk premium or the return on the market, whichever one you solve for, is going to be static. And so in this case, I'm just going to solve for the market risk premium. And I have set up my CAPM equation where 12.42% is equal to 3.4% plus a beta of 1.08 times that market risk premium. And some of you have heard me say return on the market. What's that? Remember, the market risk premium is return on the market minus the risk-free rate. So you could plug in, instead of MRP, you could plug in R subscript M for return on market minus R subscript F for a risk-free rate, and then solve this problem pretty much the exact same way. Okay, I'm going to solve for market risk premium in step one because that's my unknown variable. I get 8.35%. And then since it's static or constant, I can use it in another CAPM equation to figure out what the expected return on the portfolio is. Okay, because the CAPM works for both individual stocks and also for a portfolio. So to find the expected return of the portfolio, I'll use the same RF. RF is constant and static, plus beta of the portfolio. Now that beta portfolio has to be very specific. So that's where the change is, and that's where that 0.4 comes in. Multiply it by that same market risk premium from equation 1, and you're going to get 6.74%. So I expect 6.74% for this portfolio. And that makes complete sense considering that this portfolio has both a risky stock and a risk-free stock. So you expect it to be significantly lower expected return than what the return on the stock was. So 6.74% is significantly lower than 12.42%. In fact, you're getting close to just half. So that makes a lot of sense. Now, with problem number 7, we're going to discuss another interesting concept about betas. And one of the things you really want to know here is that the beta for the market is 1, right? And that's kind of like the standard, right? So, and the reason for that is because beta measures how the market moves with something else. So the market's going to move with itself perfectly, right? So it's going to have a perfect correlation with itself, and that's why you get 1. So in other words, if the market goes up 1%, the market's going to go up 1%, right? That would just kind of make sense. Now, you'll want to know that information to solve for this problem. Stock J has a beta of 2.08 and an expected return of 18.1%, while stock K has a beta of 0.43 and an expected return of 5.3%. You want a portfolio with the same risk as the market. What is the expected return of your portfolio? Okay, so in this case, what you really need to know is that you can, and this comes straight from the lectures, that you can figure out the beta for a portfolio by adding up the weighted betas for each stock. Okay, and so in this case, I'm going to set up my equation where beta of my portfolio is going to equal the beta of the market. They told me it has the same risk as the market, and I just told you before we started this whole problem that the beta for the market is 1. So I already know that the beta of my portfolio is going to be 1. Now, the beta of J times the weight of J plus the beta of K times the weight of K has to equal 1 as well. So if I fill those in, I get 2.08 weight of J plus 0.43 weight of K. Now, I can't solve this equation as it is because I have two unknowns, the weight of J and the weight of K. So listen up. This is when you can throw in a really cool math trick, which is basically if I know the weight of J, then I can figure out the weight of K because it's going to be 1 minus the weight of J. Why? Think of 1 as 100%. And if you take out whatever J is, whatever's left over is going to be K. Right? So if you got a big pizza pie and it's got 12 slices in it, and I tell you that I'm going to eat 4, then what's going to be left over is 8, right? So you can figure out 1 minus how many I'm going to eat, and that's, my percentage, which would be 33%, and you'll find out that 67% is left over. It's the same kind of idea, right? So we do actually only have one variable here, and it's the weight of J. So what I'm going to do is have 1 equal to 2.08 weight of J plus, in parentheses, 1 minus the weight of J times 0.43. Now I need to expand that out to where that is 2.08 weight of J plus 0.43 minus 0.43 weight of J. I'm going to combine those weight of J's, and I'm going to move that 0.43 over to the other side by subtracting both sides by 0.43, and that's how I get 0.57 equals 1.65 weight of J. If I divide both sides by 1.65, I get weight of J equals 34.55%. Okay, whatever's left over is weight of K, so 1 minus 0.3455 gives me 65.45%, and now I have both the weights. So step 1 was all about getting the weights. But they don't care about beta as far as the question here. They're asking, what is the expected return on your portfolio? So all we did in step 1 was get the weights. But just like you can find the beta for a portfolio by adding up the weighted betas, you can find the expected return for a portfolio by adding up the weighted expected returns for each individual stock. So now that we got the weight of J and the weight of K, we'll plug those in, and they told us the expected returns, which were 18.1% for J, and it was 5.3% for K. So we will add up those weighted betas, and we're going to get 9.72% for expected return for the portfolio. So this is a really good problem that teaches you both to understand that the beta, that the beta for the market is 1, and that the equations for the expected return for a portfolio and for the beta of a portfolio both are adding up the weighted components for the portfolio, whether that's the beta or the expected return. Now, conceptually, number 8 is one of the harder problems. Hopefully, I'll break this down to where it makes a little bit more sense. So you've got the risk-free rate equal to 3.4%, and the expected return on the market is 13.4%. Stock A has a beta of 1.2 and an expected return of 15.4%. That's important, right? Stock B has a beta of 0.87 and an expected return of 10.8%. So are these stocks correctly priced? Why or why not? So now you've got these quoted prices, okay, where you've been quoted a price of 15.4% for A, and you've been quoted 10.8% for B. Now, you're going to want to find out whether or not those are good quotes, and to do that, you're going to use the CAPM. So if I use the CAPM and figure out what they really should be valued at, I'm going to get 15.4% for A. Okay, I've just basically plugged and chugged information there, and 15.4% is exactly equal to what they told me in the problem. So then A is going to be correctly priced. It's going to lie right on the security market line, and it's correctly priced. Okay. However, when I look at B and I solve, I get 12.1%. Okay, so the CAPM tells me 12.1%, and the quote tells me 10.8%. So which one's better? Or other way of saying this is stock B overpriced or underpriced? Well, it's going to be overpriced, and that seems a little weird in some contexts, but you have to remember that they're telling you you're going to get a 10.8% return, but you should be getting a 12.1% return. Okay, so the price would need to come down before you would actually get the return that they're telling you you're supposed to get. Okay, so in that way, that's why it's overpriced. So if the CAPM is higher than the quoted return, then it's overpriced. If the CAPM is lower than that quoted return, then it's going to be underpriced. Okay, and that's really what you want to remember to get question number 8 correct. Number 9 is kind of your standard deviation problem that you've seen before, but it's kind of on steroids. It's a little bit more complicated. Why? Because the real world is actually a little bit more complicated. And so you can also have different states of the economy. Sometimes you have a boom cycle. Sometimes you have a recession. Sometimes things are going normal. In this case, we're going to look at both a normal state of the economy and a recession. So given the following information, what is the standard deviation of the returns on a portfolio that is invested 40% in stock A, 35% in stock B, and the remainder in stock C? Okay, now this problem is a little bit tricky. Okay, so you're going to want to do this math probably by hand instead of using your calculator. So let's go and look at step 1. The first thing you're going to do is find the expected return for the portfolio in the normal state of the economy and also for the recession, right? Remember, you can do this just by summing up the weighted expected returns. So if you know there's 40% for stock A, which I didn't get from that's not coming from the graph, that's coming from the problem written above. Remember, 40% in stock A times 19.4% plus 35%, which is coming from the question above, not from the graph, times the 13.6% for stock B, which came from the graph, plus what's left over. Remember, you can do 1 minus whatever, and whatever's left over is going to be left for C, right? So you take out A and you take out B, so 1 minus 0.4 and minus 0.35, and that's going to leave you with 0.25, right? And so that's going to be 0.25 times 0.096. You add all those together and you're going to get an expected return for the portfolio in the normal state of the economy of 14.92%. Now for the expected return of the portfolio in recession, all the weights will be the exact same. So 40%, 35%, and then 1 minus those, or 25%. And but you're going to have different expected returns, right? So negative 18.9% for A, 2.1% for B, and negative 5.6% for C. Add all those up, and you're going to get a negative 0.082250, or what's about a negative 8.2%. So, next thing you're going to want to do is get the expected, to get the average return. In other words, in step 2, you're getting the average expected return for the portfolio, and that's just going to be using the weights of whether or not you're in a normal state of the economy or a recession. So this time the weights are coming from the graph, not from the question, right? So 40% times 14.92% for the expected return of the portfolio in the normal state, and then 60% times the expected return of the portfolio in recession, which is that negative 8.2%, and you're going to get 0.010330, or right around 1%. Okay. Now, then to get the standard deviation, you obviously got to get the variance first. And in this case, notice that there's nothing, there's no all of this over n minus 1. And the reason why is because in this case, you have weights. And so to do this, you're going to take that 40% times 0.1492, which is the actual return, minus the average squared. So there's your square difference, plus 60% times the square difference for the recession. So that's where you get that negative 0.08225 minus that average you got in step 2 of 0.010333, and square that, right? So in this case, you don't have it all over n minus 1. Your variance is going to be 0.012857. If you take the square root of that, you'll get 11.34%. So notice that there is a fourth step that's kind of digs a little bit into the territory of question number 10. Okay, so that's the one that's going to have a whole lot of math involved, and you're going to have to keep track of all of it if you want to get the right answer on that problem. Now let's move on to number 10. Number 10 has to do with that idea of risk-adjusted return. A little bit like the coefficient of variation that we talked about before, but in this case, if you notice, we're going to actually put return over risk instead of risk over return like we did with coefficient of variation. In fact, we're going to use a very specific risk-adjusted return ratio known as the Trainer ratio, which is going to take the expected return, subtract the risk-free rate, and then have in the denominator the beta, right? So first thing we're going to do is see what information we have. Stock J has a beta of 0.83 and an expected return of 9.1%. Stock K has a beta of 1.6 and an expected return of 16.9%. So what is the risk-free rate if these securities both plot on the security market line? Now, what that's basically saying is that you can set the risk-adjusted returns equal to each other, or the Trainer ratios equal to each other in this situation, right? If they both stocks plot on the security market line, then you're going to be able to set their Trainer ratios equal. Now, when you set those Trainer ratios equal, the one variable you're going to know right off the bat that you don't have is the risk-free rate, and it's actually on both sides of the equation. So you're going to have to somehow get risk-free rate on one side of the equation. what I did is my first step was I cross multiplied, meaning I multiplied both sides by 0.83 and both sides by 1.67. And then you get some cancellation out, and you're going to get 1.67 equals 0.091 minus RF equals 0.83 times 0.169 minus RF. And then you got to extend those out, and you're going to, finally get a number minus a coefficient in front of RF on both sides of the equation. You're going to want to combine the RFs. So I added the bigger RF over, so I added both sides, added 1.67 RF to both sides, and then I subtracted 0.14027 from both sides, and I was left with 0.0117 equals 0.84 RF. Divide both sides by 0.84, and I get RF equals 1.39%. Okay, so that's how you would work a problem like that. And it's just a really good conceptual problem using Trainer ratios and making sure that you understand if they both plot on the security market line that you can set those two Trainer ratios equal. And in this case, the dictation that I'm using or the notation that I'm using for a Trainer ratio is just R divided by R in brackets. Okay, and for me that's what I do to remind myself that I'm looking at return over risk, right, or a risk-adjusted return. And then finally, our last problem, which is number 11. You currently own a portfolio valued at $200,000 that is equally as risky as the market. Given the information below, what is the beta of stock C? So you look down at this graph and you're like, oh my gosh, I've got 3 unknown variables. What am I going to do? Well, let's take it through and see what we need to do. I'm going to show you with step 1, which isn't even necessary, that you've got a little bit more information than you thought. One thing you need to remember is that if the beta of a portfolio is, as risky as the market, that beta of that portfolio is going to be 1, because the beta of the market beta is 1, right? Another new concept to make sure that you understand too is, what is the beta of a risk-free asset? The beta of a risk-free asset, okay, is going to be 0. There's no risk. Okay, so that's important to know too. So let's keep that in mind as we go through this problem. So to get the value, that one question mark in the middle column there, of the risk-free asset, we can just subtract, right? We know what the total amount is, and we're going to subtract off everything and see what's left over, and we're going to get $29,000 left over. Okay, so we could plug in $29,000 there to figure out the weight, for the risk-free asset, but that's not going to be important, and you'll see why in step 2. Now, to get the of stock C, let me say that again, to get the beta of stock C, we're going to have to set up an equation like we did in a previous problem with the beta of the entire portfolio equal to the beta of the market equal to 1, and then you've got these weights, right? And we're going to sum up the weighted betas. So we're going to have the weight of stock A times its beta plus the weight of stock B times its beta times the weight of stock C plus its beta times the weight of the risk-free asset times its beta. Now I put a big X through that. Now why would I do that? The reason I did that was simply because what's the beta of a risk-free asset? It's 0. So I don't even have to figure out the weight. That whole term's going to go away, right? Because whatever the weight is, I'm going to multiply it by 0 and it's all going to go away, right? So you didn't really even have to do step 1. Now how are you going to find these weights? Well, in this case, they didn't give me a percentage, so I got to figure out the percentage. I know what the value is for each stock, and I know the overall value of the portfolio, so I can just use a ratio and get a percentage there. So my weight of A, for example, is going to be 53,600 divided by 200,000. My weight of B is going to be 41,400 divided by 200,000, and my weight of C is going to be 76,000 divided by 200,000. So that's how I get the weights. I'm going to multiply those times their betas, except if you notice, I've got an unknown variable here, beta C. So what I'm going to end up with is 1 is going to be equal to 0.32428 plus 0.20286 plus 0.38 beta of C. Okay. Now if I subtract off the other numbers, I'm left with 0.47286 equals 0.38 beta C. If I divide both sides by 0.38, I get a beta of C equal to 1.24. Okay, and so that is the last problem for this part 1 of your test guide for exam 4. if you have any questions, it's probably one of the best things you could do is go back and listen to the lecture 4.1 where we discuss some of these topics, especially some of these equations. But this is the information you'll need to know, and you should expect to see the vast majority, if not all, of these problems on exam 4.